Whenever we tackle cell biology, I feel like we always end up talking about walls.
Barriers.
Exactly, barriers. The lipid bilayer as this gatekeeper that keeps all the chaos out. It's a very defensive way of looking at it.
It is.
But I was reading through the research for today, and I found this metaphor in one of the papers that it really stopped me in my tracks.
I think I know the one you mean. It's pretty poetic for a biochemistry paper.
It really is. It said, "Not all lipids are bricks. Some wear sugar crowns and speak the language of cells."
That's a great line.
And I just sat with that for a second. Because we think of lipids as just, energy storage or the mortar holding the cell together. But this suggests they're communicative.
Oh, absolutely. And It's not just poetry. It's chemically accurate. If your standard phospholipids are the drywall of the cell, then the lipids we're talking about today are the doorbell, the mailbox, the whole communication setup.
That is a big upgrade from drywall.
It's a huge one. We're talking about glycosphingolipids.
Which is a massive mouthful of a word.
It is a tongue twister, yeah. But these are the molecules that turn a cell membrane from, say, a plastic bag into a real communication hub. Without them, your cells are basically mute.
So that's our mission for today then. We want to move past that simple lipid bilayer 101 picture and look at the actual architecture of these royal lipids.
Right. How they're built, how we classify them.
And the naming is a labyrinth, I have to say, and ultimately why they matter so much.
And to do that, we have to start right at the foundation, the backbone.
The backbone. Okay, so usually when we talk lipid backbones, the answer is always glycerol. That's the standard, isn't it?
For most of them, yes. Glycerol is built from 3 carbons. It's small, it's flexible, very efficient.
So it's like the Honda Civic of lipid backbones.
Yeah.
Reliable everywhere.
That's a good way to put it. Gets the job done. But here's the key idea from the sources today. Sugar likes sphingosine, not glycerol.
Okay, sugar likes sphingosine. So why? Why does sugar shun the reliable Honda Civic?
Well, it comes down to structural integrity. Glycerol is flexible, which is great for a fluid membrane, but if you want to hold up a big, heavy, complex carbohydrate, a crown,
you need something stronger.
You need a steel beam, not a wooden slat. And that steel beam is sphingosine.
Sphingosine.
Correct. It's an 18 carbon amino alcohol. Just think about that. 3 carbons for glycerol, 18 for sphingosine. It's a beast.
So it's just physically bigger, more rigid.
And it has a different way of connecting things. It's an amino alcohol, so it has a nitrogen atom. That lets it form an olamide bond, which is way more stable than what you see in standard fats.
Okay, let me get this visual straight. We're building something tall, something elaborate, these sugars. So we ditch the wood frame of glycerol, and we bring in the industrial steel of sphingosine.
That's the logic exactly. Without that sphingosine backbone, it's not a glycosphingolipid.
Got it. So we have our steel girder, but we don't just slap a sugar on it yet, do we? There's an intermediate step.
Right. You have to stabilize the base first. You take that 18 carbon sphingosine and you attach a long chain fatty acid to it.
And that connects to the nitrogen, the amino group you mentioned.
Precisely. That's the anchor point. Once that fatty acid is locked on, you've created a molecule called ceramide.
Ceramide. Okay, I've seen that word everywhere. It's all over the skincare aisle.
You absolutely have. It's marketing gold, but it's based in real biology. In skin, they're the glue. But for what we're building today, think of ceramide as the blank canvas.
Or like the stem of a flower. It's waiting for the blossom.
Exactly. It's the potential for communication, but not the communication itself.
Okay, so let's get to the blossom, the decoration. This is where my notes get a little messy because the classification just branches off everywhere.
It can seem that way, but we can simplify it. Just split the family tree into 2 main branches. The only question you need to ask is it electrically charged?
Charged versus uncharged. Okay, let's start with the uncharged ones.
The neutral crew. The neutral glycosphingolipids. These are built by just adding simple uncharged sugars to that ceramide stem. Let's say we start with just one, a single monosaccharide.
The sources call this a cerebroside.
That's the category. And if that single sugar is glucose, you have a glucose cerebroside.
And if it's galactose?
Galactose cerebroside. Simple as that.
For once, biochemistry is literal. I appreciate that. But cells rarely stop at just one sugar, do they?
Not usually. And as soon as you add another one, say, you attach a galactose onto your glucose, the name changes.
Right. Glucose plus galactose is lactose.
It is. So the molecule is lactosylceramide. But the category, it graduates.
Yeah.
It's no longer a cerebroside. It becomes a globoside.
Globoside. It sounds bigger, more globular.
That's the idea. Is any ceramide with 2 or more of these neutral sugars attached. But the key, as you said, is the charge.
Or the lack of one.
Exactly. Glucose, galactose. These are neutral molecules. They don't carry a charge. So cerebrosides and globosides are electrically neutral. They're just there.
Providing structure, spacing, but not bringing any electricity to the party.
Not bringing a spark. But of course, the cell needs sparks, especially in the nervous system. You need charge to move signals.
And that brings us to the second branch of the family tree.
This is where the story gets really interesting.
My notes just say, the entry of Nana. It sounds like a character from a soap opera.
It is a dramatic entry. NANA stands for N-acetylneuramic acid,
A bit of a mouthful.
which is why most people know it by another name, sialic acid.
Okay, sialic acid. So what makes Nana the game changer?
She brings an acid group, carboxylic acid. And at body pH, that means NANA carries a negative charge. As soon as you attach NANA, you transform the molecule. It becomes a charged beacon. It creates a ganglioside.
Ganglioside. That sounds much more serious than globoside.
Well, the name comes from ganglion, a nerve cell cluster. These are absolutely critical in the nervous system. That negative charge is key for how neurons function.
So a nerve cell is covered in these things, but the classification, I saw this code, GM3, GM2, GM1, and the numbering feels backward.
It's a common confusion. You'd think GM1 would be the simplest.
Exactly, Model 1. But it seems to get more complex as the number goes down.
It's a quirk of history.
Yeah.
It's based on how fast they moved in an old experiment. GM3 was the smallest and fastest, so it got the 3. GM1 was the big slow poke.
So it's a race ranking, not a construction manual.
Right. Let's just walk through how they're built. We start with the simplest one, GM3.
And what does GM3 look like?
It's our base, ceramide, a glucose, a galactose, and then you add a single nanomolecule. That's it.
Okay, base model plus Nana, GM3.
Now, to level up, the cell adds another sugar and acetylgalactosamine.
Not to be confused with Nana.
Correct. It's a complex sugar, but it's not acidic. When you add that, the molecule becomes GM2.
So we added a piece and the number went down. Got it.
And to reach the most complex one in this series, we add one more galactose molecule to the end of the chain.
And that gets us to GM1.
Biggest of the 3. It's a monster. But because of that one nanomolecule, every single one of them, GM3, GM2, and GM1, carries that negative charge. They're all electrically shouting.
Is Nana the only way to get that charge?
There is one other way mentioned, though it's a bit different. You can make sulfatides,
Which involves sulfur, I'm guessing.
a sulfate group. You take a simple cerebroside and you attach a sulfate group. Sulfate is also negatively charged. So the acidic branch includes both gangliosides with NANA and these sulfatides.
Okay, so we've built the whole inventory, the neutral crew and the acidic crew. But where do they sit? What's the context?
Location is everything. And there's a very strict rule here. These lipids are extroverts.
Extrovert.
They only face one way, out,
Towards the rest of the world.
always. Their tails are buried in the membrane, but the sugar crowns always point into the extracellular space. They never, ever face inwards to the cytoplasm.
So if you're inside the cell looking up, you don't see any of this.
Nope. You just see the boring tails. You have to be outside to see the crowns.
And when you have millions of these cells together, all with their crowns pointing out, you're creating a kind of sugar forest.
A layer. We call it the glycocalyx.
The glycocalyx.
Calyx means a husk or a shell. It's literally a sugar coat. A fuzzy, sticky, carbohydrate-rich atmosphere around every cell.
An atmosphere. But biology doesn't build something this expensive just for decoration. What is this coat doing?
It is the cell's ID card. It's how your body knows that a cell belongs to you. Think about your immune system patrolling for invaders.
Right.
How does it know your liver cell is your liver cell?
It reads the sugar crown.
It physically interacts with the glycocalyx. The specific pattern of sugars, a GM1 here, a globoside there, it acts like a barcode. If the barcode scans itself, the immune cell moves on.
And if it doesn't,
Then it attacks. Or in other cases, that sugar code is a docking station, a lock waiting for a key, like a hormone.
so when the paper said they speak the language of cells, that wasn't an exaggeration at all.
Not at all. They are the vocabulary. Without that specific architecture, the cell goes mute.
Can you give us a really concrete example? Where does this reading process make a life or death difference?
Well, our own body reads the codes, but so do pathogens. They've learned the language. Take cholera.
The disease?
Yes, the cholera toxin doesn't just attack randomly. It's looking for a very specific address. It specifically looks for GM1.
The most complex one we talked about.
The penthouse model. The toxin uses GM1 on your intestinal cells as a landing strip to get inside.
Wow. So the very thing that's supposed to identify the cell gets hijacked.
It's a biological backdoor.
Yeah.
If those cells had GM2 instead of GM1, the toxin would likely just bounce right off. It wouldn't recognize the address.
That's incredible. The difference between GM1 and GM2 is just one single sugar molecule.
One terminal galactose.
And that one tiny difference determines whether a deadly toxin can bind or not.
It's terrifying, but it's also amazing. That's biology in a nutshell. A game of shapes and charges.
So let's try to wrap this up. We started by ditching the standard glycerol backbone.
Right. We needed the steel girder, sphingosine, to hold up the crowns.
We attached a fatty acid to that, making ceramide our blank canvas.
And then we started painting with sugars.
Yeah.
First, the neutral cerebrosides and globosides.
And then came the charged ones. We brought in NANA to make the acidic gangliosides, GM3, GM2, GM1, the powerhouses.
All of them pointing outward, creating the glycolipids, that sugar coat that tells the world, I am here, and this is who I am.
It really does change how you picture the body. We're not just bags of water. We're coated in this sticky, informative sugar layer.
And it's a dynamic language, constantly being updated.
Well, that is about all the time we have for this deep dive. I hope this gives you a different perspective on the fat in your cells. It's not just sitting there. It's doing the hard work of communication.
It is a busy world down there.
It certainly is. Thanks for listening, everyone. Next time you read about cell recognition, just remember, you are watching the sugar crowns at work. We'll see you on the next deep dive.